Good morning to everyone. Myself, I am Suryanarayana, working as an assistant professor in PB Orbits Kavali. Today in this class, I am going to discuss about forces in rolling and power requirements. First of all, for these rolling forces, I am taking flat rolling as a consideration and its analysis. First of all, we know that the process of rolling, the work part is passed in between two opposing rollers. One is rotating in counterclockwise, another one is clockwise direction. In this figure I am showing that the direction of workflow in forward direction and work. Next, figure 2 explains side view of flat rolling, indicating before and after thickness, work velocities, angle of contact with rolls and other features. In this, the process is same, but here some parameters are indicated. T0 initial thickness, Tf will be the final thickness, and rolling speed is Vr. Next, in this, some point, that is the contact is made in between two opposing rollers, that is angle of bite or angle of contact. The total length of contact is L, capital L, that is the contact length, and theta is the angle, and capital R is the roll radius, P is the roll pressure, V0 is the initial velocity, Vf will be the final velocities. This is about rolling parameters. In analysis, coming to flat rolling is illustrated, that means we saw two figures, one is rolling process and parameters in rolling, that means thickness, velocities and before and after work. It involves the rolling of slabs, strips, sheets and plates, work parts of rectangular cross section in which the width is greater than thickness. That means the rolling process is used for reducing the thickness. So for that reason, thickness is reduced after the work and width is increased. That is the phenomena. Next, in flat rolling, the work is squeezed between two rolls. Squeeze means reducing thickness. Here only criteria used for reducing the thickness. Next, so the thickness is reduced by an amount called the draft. Small d indicated for draft, that equal to T0 minus Tf, initial thickness minus final thickness. Draft is the amount was get by subtracting the final thickness from initial thickness, where T0 is the initial thickness, Tf is final thickness. Draft in all are in mm. Next, draft is sometimes expressed as the fraction of the starting stock thickness. T0 is the starting stock thickness or initial thickness or original thickness, called the reduction, small r, that equal to d by T0. D is the draft, T0 is the original thickness or initial thickness or starting stock thickness. That is the expression 2. First expression is draft, T0 minus Tf. Second one is reduction, that is small r, that equal to d by small d by T0. Two expressions are there. After that, in addition to thickness reduction, rolling usually increases working width. For that is called spreading. It tends to most pronounced with low width to thickness ratio. For conserving this matter, volume of metal exiting the rolls equals to volume of entry. The volume that includes thickness, width, length before and thickness, width, length after. T0, W0, L0 equals to Tf, Wf, Lf. And next, Similarly, before and after volume rates, material flow must be the same. So before and after velocities can be related. T0, W0, V0 that equal to TF, WF, VF, that is expression 4. Here V0, VF are the entering and exiting velocities. Since the metal flow is continuous, there is a gradual change in velocities of work between the rolls. However, there is one point along the arc where work velocity equals to roll velocity. Work velocity, that is V0, that equals to roll velocity VR. That point is known as no slip point. On either side of this point, slipping and friction occur between roll and work. The amount of slip between the rolls and the work can be measured by means of forward slip, that is slip is indicated by capital S, that equal to Vf minus Vr by Vr. Vf is the final velocity, Vr is the rolling velocity, that is forward slip in meter per second, velocity is in meter per second, slip. And next, true strain experienced by the work in rolling is based on before and after stock thickness. In equation form, epsilon that equal to ln T0 by Tf, that is true strain. We already know that strain change in length to original length. Here before thickness divided by after thickness, you will get true strain. After that, the true strain can be used to determine the average flow stress, that is YF. YF that equal to K epsilon power n divided by 1 plus n, that is expression 7. Next, the average flow stress, that is YF, is used to compute estimates of force and power in rolling. Friction in rolling occurs with a certain coefficient of friction, and the compression force of the rolls multiplied by the coefficient of friction. We already know that coefficient of friction is indicated by mu or m, results in a friction force between rolls and the work. On the entrance side of no slip point, I was already told you, where the work velocity is equals to roll velocity, that point is known as no slip point. There is a limit to the maximum possible draft that can be accomplished in flat rolling with a given coefficient of friction, that is D max. D is draft in maximum direction, m is the coefficient of friction, m square r. And next, the equation indicates that if friction were 0, draft would be 0. There is no friction here in between two rolls, and work will also 0, and it would be impossible to accomplish the rolling operation. Coefficient of friction in rolling depends upon lubrication and which type of work material you are using and working temperatures. These are the affecting factors of rolling. In cold rolling, the value is around 0.1. In warm working, typical value is 0.2. In hot rolling, m, that is around 0.4. Hot rolling is often characterized by a condition called sticking. The condition occurs in the rolling of steels and high temperature alloys. When sticking occurs, coefficient of friction mu can be as high 0.7. And next, coefficient of friction sufficient to perform rolling. Friction is very necessary parameter. Friction plays important role in rolling process because if friction is 0, draft is 0. In that time there is impossible to maintain the friction between two rolls can be computed by integrating the unit roll pressure. Force F equal to W integral 0 to L PdL. P is the pressure, dl is the change in area. Ninth expression, the integration requires two separate terms, one for either side of the neutral point. Variation in roll pressure along the contact length is significant. For this, pressure reaches maximum at the neutral point. As again friction increases, maximum pressure increases related to entrance and exit values. As friction decreases, neutral point shifts from away from entrance towards to the exit point. And next, an approximation will be taken. Here Yf is the average flow stress, force required in rolling F, that equal to YFWL. Here Yf is average flow stress in megapascals and the product WL is the roll work contact area mm square. That is the typical variation in pressure along the contact length in flat rolling. Why we are making the peak pressure, that is the graph plot in between pressure to length. The direction of flowing or direction of rolling in forward direction. Here the no slip point where the work velocity is equals to roll velocity, that is no slip point. S equal to the forward slip will be S equal to capital S equal to Vf minus Vr by Vr. But here no slip point occur only at neutral axis, that is peak pressure. Next, contact length can be approximated by capital L, that equal to square root of capital R roll radius in brackets T0 minus Tf, that is expression 11. And the torque in rolling can be estimated by assuming that the roll force is centered on the work as it passes between two opposing rolls. That acts one half of the contact length L, that is T, that is capital T, torque, that equal to 0.5 FL, force into length. If the force or the power required to drive each roll is the product of torque and angular velocity, then the equation angular velocity omega, that equal to 2 pi n, then where n is speed, after substituting that value in torque equation, then it can change like that, P, that equal to 2 pi n FL. In that place 0.5 we are placing 2 pi n omega angular velocity, power in joule per second, n rotational speed, F rolling force, L is the contact length. That is the equation for forces required in rolling and power requirements. P, that equal to 2 pi n FL. Thank you students, thanks for watching.